I'm Ben.
I'm Nico.
I'm Gokul, and our project is FPGAirPods, and as the name implies, we're doing active noise cancellation.
So in order to implement active noise cancellation, we had to have a physical system to test on. And the physical system that we envisioned involved an ambient noise microphone, a feedback microphone, and a speaker between the two. The speaker would output an anti-noise signal, and the feedback microphone would pick up the sum of that anti-noise signal and whatever signal was coming in from the environment, the ambient noise. Our goal was to bring this feedback microphone signal down to zero, meaning that the ambient noise has been canceled by our anti-noise signal. In order to implement that, we have a physical system that looks like this. So we started with a peanut butter container that we washed out, and we lined with some noise dampening foam, which you can see is the black stuff. And we also have some shipping foam that we lined in the back and the front of the peanut butter container. Right here is where we put our speaker. It's just a regular portable speaker that we fit inside there. And you can see on the end here, on the outside, we have our ambient microphone. And similarly on the other end, our feedback microphone is mounted. Along with the feedback microphone, we have just a regular pair of earbuds with their microphone lined up right next to the feedback microphone. So in our demos, we'll be recording from that microphone so you can hear what it sounds like inside the cavity and that our cancellation is indeed actually making an audible difference. The other aspect of our hardware setup is the music input. So we wanted to be able to overlay music on our anti-noise signal. And basically we just have a headphone jack breakout board that we then have a little bit of circuitry to bring the values into the range that the FPGA wants to interpret. And then we run these to the onboard ADC on the FPGA. Now all these signals, so this signal gets converted into a 16-bit signed signal to match the signal that comes in from the two microphones. The two microphones communicate over I2S, which is a digital protocol, and we wrote an I2S module to communicate with both these microphones. One is set up on the right channel, one is set up on the left channel. So we can get 16-bit signed samples from both of those at about 65 kilohertz with our I2S module.
So I'm going to talk about kind of the overall flow of our system. So what happens is once we receive the feedback signal and the ambient signal that we receive from our digital microphones and pass through I2S, we're going to do some processing on them. And essentially the first step of that processing is applying a DC offset remover so that we can center the signals around zero. And next we also low pass the signals with a cutoff of 700 hertz because we mainly are focused on canceling frequencies under 700. And after that, we essentially pass the feedback signal into our error calculator module. And that error calculator module is responsible for keeping track of how good our system is doing at actually actively canceling the signal. So once we have that error, we pass it into the LMS module, which uses the normalized least mean squares algorithm that Nico will kind of go in depth into later. But essentially, it's going to use the error to update the coefficients of our FIR filter based on how well we're currently canceling the signal. Once we have those updated coefficients, the FIR is going to apply a filter using those coefficients to the ambient noise signal in order to generate an anti-noise signal. So that anti-noise signal gets played out of the speaker within our system in hopes of canceling out the noise that makes it into our cup system.
For our project, we use NLMS, which is a variation of the least mean squares algorithm. This is an adaptive filter that takes in an error signal, in our case, the feedback mic, and it continuously updates the coefficients to minimize that signal. It does this by using gradient descent, which if you're familiar with machine learning, it's the foundation of a lot of models. And in our case, since we're using NLMS, instead of having a learning rate during our gradient descent step, we instead take 1 divided by the norm squared of the previous samples. And what this allows us to do is converge easier since we're basing our learning rate on the size of the input. Once we have converged, we lock the coefficients, and that allows us to play music over top of it by adding it to the anti-noise signal, thus giving us the final result shown in the demos. For our first demo, we'll be playing a couple of sine tones, and you'll be able to hear the difference between noise cancellation on and noise cancellation off. In addition, when we're changing the sine tones, you'll be able to hear the error blowing up and the system basically reconverging to the new coefficients to minimize it.
Our second demonstration is going to be very similar to our first, but this time we're going to have music playback in the equation. So essentially, every time our system converges on a new sine tone, the music is going to continue or start playing, and you're going to be able to hear the difference between music playback with cancellation on and music playback with cancellation off.